Thank you, Rukmini. I have been many times to Bangalore, but I have never been to ICTS. So thank you very much for the invitation. I'm very glad and very impressed by the facilities. And I was talking to Carlos before, and he was telling me about these mile sandwiches that are announced in the US. So this is like a mile blackboard. This is the longest blackboard I have seen. So I'm a bit sorry that my talk will be mostly a presentation, but although I'll write a bit in this great blackboard. Okay, so I want to tell you about higher Teichmuller spaces. These are generalizations of the usual Teichmuller space of a surface, but let me put this in a context. And so the context here is we start with S, an oriented, a smooth, compact surface of genus bigger than 1. And then we consider its fundamental group, pi 1 of S. And we will consider a connected real semisimple Lie group. Actually, I say real or complex. What I mean is that, yeah, so is a semisimple Lie group that could be real or complex. And in fact, the whole theory appropriately can be extended to reductive groups and also to non-connected groups. But today I will focus on connected and semisimple Lie groups. And so we are interested in studying representations of the fundamental group of S in G. So this is simply a homomorphism from pi 1 of S to G, a group homomorphism. And the set of all these homomorphisms is an analytic variety. It's algebraic if G is algebraic. And then, of course, as usual, we're interested in equivalence classes of representations. So the group G acts on the set of all homomorphisms by conjugation by an element in G, right, in this way. So you have a representation, you can construct another representation, and like that. And of course, we're interested in the set of equivalence classes, but that is typically for when G is compact. The set of equivalence classes is a nice manifold. It's a nice variety. Excuse me. May have singularities, but it's a nice variety. But if G is non-compact, and in what I'm going to tell you today, the focus is on non-compact Lie groups, then you have to remove certain representations in order to get a nice space, a nice topological space, to avoid non-Hauser phenomena, right? And so the condition is that of the representation be reductive, which simply means that if you post-compose the representation with the adjoint representation, then that decomposes, so this is a representation in the Lie algebra of G, just decomposes as a sum of irreducible representations, right? So that's one definition of reductive representation. And so now you consider the set of all reductive representations that I denote by this plus here. And this is the space we're interested in studying. The moduli space of representations is the quotient of all the reductive representations modulo G, sometimes referred as the character variety of the fundamental group in G. Yeah? You can also view this, in fact, as, you know, this condition of productivity appears also naturally from the GIT point of view. If you think of the quotient of this affine, take all the representation, not the reductive ones, and then that the reductive, the GIT quotient is exactly this. Okay, so this is analytic variety, which is algebraic if G is algebraic. In fact, is complex if G is a complex group. Has a naturally complex structure coming from the group G if G is complex. And this is the focus of attention of these talks. So in general, one is interested in the topology and geometry of this character variety. This is, of course, a vast question. And I will focus in this talks basically about not just the, I mean, a very modest question about the topology, which is about components of this variety, but in particular of special components, components that share properties, have properties in common to Teichmuller space. I will explain. So, but in any case, the approach that I will take will be an approach in complex algebraic geometry. Even though the group G, most of the time, will be a real group, but the complex nature of the problem comes from the fact that I will choose a complex structure on the surface, so to make it a Riemann surface. And so that is, so the problem will be reduced to a problem in algebraic geometry, in complex algebraic geometry, by means of the theory of Higgs bundles. Yeah? So let me explain, so what a Higgs bundle is in this general context. And please feel free to stop me and ask questions. And in particular, since it's very easy to go very fast with this thing here, right? And so, as you were encouraged, in particular the younger people, the older ones can also ask, huh? But the younger people to ask and interrupt me as many times as necessary. So we choose a complex structure on the surface. So now I'll denote it by X. So X is a compact Riemann surface, a closed Riemann surface, no boundary. And then I want to, in fact, take a group G now, which is complex semi-simply group, right? So no, it's not any group, but it's a complex semi-simply group. And now I choose a real form of G. So by a real form, I mean a subgroup of G, G regarded as a real group, so that GR is defined as the fixed points of a conjugation of an anti-holomorphic involution on G. So for example, if you have SLNC, right, you have SLNR or SUN, SLNR, SUN, SUPQ, all are real forms of SLNC, right? So this is so I fix G and I take a real form, and then I consider I fix a maximal compact subgroup of GR, right? Which I call HR. And once I do this, I have a whole package of things. I have what is called a Cartan involution or Cartan decomposition of the Lie algebra. This is GR is the Lie algebra of this real group that we are fixing. And so we have a decomposition of this Lie algebra in terms of the Lie algebra of the maximal compact. And then MR, which is actually orthogonal, is the orthogonal complement with respect to the killing form that I have on GR. And this decomposition has these important properties that Lie brackets of MR is in HR. Then if you take an element in HR with an element in MR, this goes to MR. So this is the Cartan decomposition and the Cartan involution of the Lie algebra of the GR. And so then we have what is relevant for us now here is we take the complexification of HR that we call H and the complexification of MR that we call M. And if you take the adjoint representation of so if you take if you take the adjoint representation of GR, the group GR in its Lie algebra, and you restrict it to HR, then it breaks in two representations. One is the adjoint representation of the group HR, and another is a representation in MR. This is called isotropic representation. And the complexification of that is a representation of H in M. And this is what we refer to this also as isotropic representation. Okay, I will be referring to this data several times, so I think it's good that I perhaps fix it here, because then this transparency will be gone, right? So we have G, let me just remind you, semi-simple, complex the group. And then we have GR is a real form. And then the choice of a maximal compact in GR, which is called, this is a maximal compact. And we have the, so what else? The Cartan decomposition. So GR in the Lie algebra of HR plus the orthogonal bit with respect to the killing form, we call MR. And then the other ingredient is the representation, the complexified isotropy representation, right? That is H in GL of M, the isotropy. So this is the package. Let me tell you that we will be interested very often, in fact, many times, not in this talk, but in general, in a situation where GR itself is actually a complex group. And let me just remind you that any semi-simple complexly group appears as a real form of its double. So you can take in G cross, if G is a complex group, you can take G cross G, and then G, there is an, you can define an anti-holomorphic involution in G cross G so that G itself appears as fixed points. So we are, by doing this, covering the situation where the group GR is complex. Okay? So we're not losing, we are doing a theory where GR can be complex or can be real and non-complex. The emphasis in these talks will be really when it is real and non-complex, but I just want to tell you that we are covering the general theory of Higgs bundles for complex groups. I haven't told you yet what's a Higgs bundle in this context, but I'm just telling you that we will recover whatever the definition is, Higgs bundles for complex groups as well. So let me get to that actually. So what is a GR Higgs bundle on the Riemann surface? So this is a pair now consisting of a holomorphic, so E, so it's an E phi, where E is a holomorphic principal H bundle over X, and phi is a holomorphic section of the bundle EM, so this EM is the bundle associated to the principal bundle via this representation, right? So we get a vector bundle whose fiber is M, and then we tensor with the canonical. The canonical case, the canonical line bundle of the Riemann surface, right? So this is a GR Higgs bundle. Okay? So in particular, if GR was complex, then the complexification of HR is GR itself, and the isotropy representation is the adjoint representation, and we recover the notion of a Higgs bundle for a complex group. Okay? Now, in order to have moduli spaces for these objects, we need there's a stability condition that emerges from geometric invariant theory, and I don't want to get into that, right? But just let me tell you the main ingredients, right? And I don't know if that. Sorry. Yeah. So these are the main ingredients actually to define stability in this context. Involves parabolic subgroups that we heard in the previous talk by Balaji. And so I want to, this is a way of phrasing how do you define the stability and so on, which is for any element in you take the Lie algebra HR and you multiply by the square root of -1, you define a parabolic subgroup PS, which is a parabolic subgroup of H, defined in this way. Of course, each of these parabolic subgroups can be obtained from the Dynkin diagram in the way that Balaji was describing before, right? The standard parabolics. So it's conjugate to one of those. But I like to think in these terms because this element S defines also, this element S defines also a character of the Lie algebra of PS, and now another ingredient that I need to define stability is the subspace MS, this is a subspace of the isotropy representation that has this growing as t tends to infinity, right? So it's a subspace of M. And so now if I have a reduction of a structure group of E, so remember that E is an H bundle, right? So if I have a reduction to PS, right? So then I can define the degree of E with respect to this reduction and to respect with this element that I am choosing, this little s here, by taking the curvature of a connection on the PS bundle and then applying the character. So this is an element in the Lie algebra. So this is a two-form. I integrated and obtained this number. There are algebraic ways of defining the degree, but this is a way that is very appropriate in the gauge theoretic context that is behind all these constructions. And this is thanks to the to Chen-Wei theory, so it's a good definition of degree. So with this in hand, with all these ingredients in hand, you can define now what stability is for a GR-Higgs bundle, and you say that a Higgs bundle, if is stable, if for any reduction sigma and for any s, such that phi belongs to this bundle. So it's in MS, remember that this element MS defined some subspace, some linear subspace of M, right? So this is, so if that, if that happens, right? So then for those reductions so that this happens, then the degree must be bigger than 0. So this is stability. And then you say is polystability basically means that, okay, if you allow equality, you have semi-stability, right, as usual. And polystability is basically that this object can be reduced to a G prime R Higgs bundle where G prime is a subgroup, a reductive subgroup, so that the reduction is as stable as a G prime R Higgs bundle. Okay, so just to give you a flavor of what is involved in question.
What is the connection induced by the reduction of structure?
No, you take you want to go back to the definition that I gave you before. This one here, yeah? Yes. You take any connection, right? You have a PS bundle, right? And you have any connection, and thanks to Chen-Wei theory, right? This defines you you know, by using the curvature of that connection, you obtain this number right here. Okay, so why am I using this definition? Let me give you another definition of degree that may be more appealing to you, right? Which is that suppose that this character of the Lie algebra here lifts to a character of the group PS, right? So then, if that happens, then you can construct, so a character of PS is a homomorphism from PS to CS star, right? So using that character, you have a line bundle. The degree of that line bundle. But it so happens that not all the, sometimes, you know, not all the characters may lift, right? So there is an issue about the characters of the Lie algebra lifting to the group, right? And in general, this is the right definition you have to take, right? There are situations where it's enough to deal with characters that lift to, if you just deal with bundles, with principal bundles, it's actually enough to deal with those characters that actually lift, right? When I say enough, this gives you the right GAT condition, right? And the right moduli space and so on. And so the character is defined as the degree of that line bundle, yeah? But so that character can be obtained from Chen-Wei theory using a connection, okay?
So is this notion of stability, GIT stability for some infinite dimensional GIT problem?
You can think like that, but it is a precise GIT, this condition, right? In particular, in the situation, let me say in this way, in the situation where actually the characters can be lift to the PS, right? This is a GIT condition that is obtained. This is a GIT condition, a finite dimensional GIT condition, right? And in fact, this is a context in which one can, let me just say something, right? And I'll come back to this in a second. But let me just say that you defined the moduli space of polyastable GR-Higgs bundles as a set of isomorphism classes of polyastable GR-Higgs bundles, or if you prefer, S-equivalence classes of semi-stable bundles and so on. And this is a complex algebraic variety. And the way actually this is proved is by means of GIT, right? And that, I mean, there are several ways. Carlos gave a construction of these things, how you construct these moduli spaces. A GIT construction, finite dimensional GIT construction, Alexander Schmidt has a construction that applies not to just these objects, but actually, after all, these objects are pairs of a bundle and a section of a certain vector bundle, right? So there are pairs in which that section can be on an arbitrary vector bundle associated, and in that context, Alexander Schmidt gives a GIT construction, right? So using the finite dimensional GIT construction, okay? Yeah. More questions about this? Okay, so, yeah, so whenever a group is a classical group, we like to think of these things in terms of vector bundles, right? Well, I don't know if we like, some people like me, we're linear algebra animals, and we like to think, in a sense, it's easier to work in these general terms, but to do things, and historically, how things have actually emerged is by using vector bundles, and whenever your group is a classical group in particular, you can do that, right? And you can understand in a better way, or actually go back to the origins of the theory, right, in terms of vector bundles. And so let me take as a first example SL and C, right? And so in that case, so let just see in that situation, what is the maximal compact? The maximal compact is SUN. So I told you that you could take actually as your real group a complex one. Here's one particular situation, right? And so the maximal compact is SUN. The complexification, of course, is the group itself. And M is the adjoint representation. And so an SL and C Higgs bundle is equivalent to a pair, V phi, where phi now is a holomorphic vector bundle of rank n. And because we are taking S and not GL, but SL, then we fix the determinant of V to be trivial. And for the same reason, the Higgs field, which now can be seen as an endomorphism, excuse me, it's a homomorphism from V to V tensor K, has to have trace 0. And so in that situation, stability is the usual notion of a stability, right, of vector bundles, and Higgs, well, in this case, adapted to Higgs bundles, which is that the degree of any subbundle has to be less than 0. Notice that I am taking SL and C, so that's why you have 0 here. So, and we don't have the usual slope condition. I mean, we have the slope condition, but in this case, the slope of V is 0, and that's why we have 0. But now this has to be checked only for the subbundles that are invariant under phi, right? Phi of V prime goes to V prime tensor K, right? So this is the condition that in the general theory, there was this subspace MS, right, determined by the parabolic. And so that is exactly the generalization of this fact here, right? And so polystability in this situation is that your vector Higgs bundle is the direct sum of Higgs bundles, all of them of degree 0, and each of the Higgs bundles being stable, okay? So this is the original notions that were introduced by Hitching in his seminal original paper, and is just similar to the theory of vector bundles as studied by Narasimhan and Seshadri, and for just vector bundles, okay? Right. Let me just say that in the general condition, you have parabolic subgroups, and it's just something that when you're dealing with a group that is complex in particular, like SL and C, one proves that is enough to check maximal parabolic subgroups. You don't have to consider all the parabolics. And so, and that's why you have to consider just subbundles, right? That is the equivalent statement of maximal parabolics. In general, meaning if you are working with real groups, right, that doesn't happen in general. You have to consider more general parabolic subgroups. In many cases, there are simplifications that tell you it is enough to consider parabolics that are of this length or something, right? So, but in general, you have to have filtrations of your vector bundle that several steps, okay? And that happens for many real groups. It's not the case for the next example that I'm going to tell you, which is also expressible in terms of maximal parabolics. But so let me give you another genuine example, in the sense that it's a real group that is not complex, okay? And that is the case of SUPQ. So SUPQ is a real form of SLNC, right, where n is p plus q and corresponds to the subgroup that preserves a Hermitian metric of signature PQ, right? And so in that situation, maximal compact is S of UP cross UQ. This S simply means that the determinant has to be 1, of course, because this is an SLNC. And the complexification of this is S of GLP cross GLQ. And the isotropic representation, oh dear, what do I say? Computer is there, yes? I would be tempted to say yes, but I don't know what it's asking. But oh no, maybe not. Yes, that's better. Yes. Thank you. So this is the situation. The isotropy representation is actually a representation that is reducible, and it has two. So is Hom from CQ to CP and Hom from CP to CQ. This is a very important example. We will come back to this, and we'll see this sort of example will have an important role in these talks. Is an example of a group of so-called Hermitian type, and this is a phenomenon. The fact that the isotropy representation decomposes in two irreducible representations is an important thing. So anyway, but in here, so what is an SUPQ Higgs bundle in terms of vector bundles is now a tuple consisting of two vector bundles, V and W, rank P for V, rank Q for W, and then there is this condition that the determinant of V tends to the determinant of W is trivial. That again comes from the SLNC thing. It comes from here. The structure group is this, right? This S. And then the Higgs fields now, because of this, the Higgs field actually has two pieces. One goes from W to V tensor K, and another from V to W tensor K, gamma, beta and gamma, okay? And now you can formulate a stability, and it's just the usual friendly condition that the degree of V prime plus the degree of W prime is less than 0 for every V prime in V, W prime in W, such that W prime goes to V prime by beta and V prime goes to W prime by gamma, right? And so again here, as I said, the theory reduces to maximal parabolic subgroups. You don't have to deal with other parabolic subgroups. And polystability is actually, in this, can be described by realizing that to this tuple, oh dear, what am I, sorry. Yeah. To this tuple, you can actually associate the corresponding Higgs bundle for the complex group, complexification of this, which is given in this way, and you can actually define polystability of this as the polystability of this SLP plus QC Higgs bundle using the definition that I gave you before. Okay, so for many classical groups, you can work out things, right? But it is interesting, as I said, for example, if you take a group that I'll come back later on, which is the real symplectic group, then, and you work this in vector bundle terms, which I'll do later on, it is not enough to check subbundles. You have to consider two step filtrations, right? Which are parabolics of a certain kind, but not all of them, but not the maximal. Okay, it's quite mysterious. There is no yet a general. It's a question about convexity, and there is no yet a general result that tells you, in general, how you can simplify these things. What are the parabolics that you need to consider? Okay. Anyway, so this is, as I said, classical groups in vector bundle terms. Now so a stability emerges in order to construct moduli spaces. If you're an algebraic geometry, that's the natural way in which the stability conditions arise by means of GAT. But if you're a differential geometer, somehow you also encounter stability in a different way, in a very fundamental way, as a condition for existence of solutions to some nonlinear PDEs, right? And so here's the theorem that is actually the context in which, when you deal with Higgs bundles, you encounter stability from that point of view. And so this is in studying, so I give you a GR-Higgs bundle, and you are interested in having a reduction of a structure group of E from H to the maximal compact. So for example, if we're dealing with SL and C right here, this is just a Hermitian metric on E. So reduction to SUN will be a Hermitian metric. So this is the generalization of a metric. So reduction from GR to the maximal compact is sometimes generally referred as a metric, right, in that sense. So you are interested, and this is how hitching, in fact, this was a starting point of hitching, the self-duality equations. And so this is, you want a reduction of a structure group that satisfies the hitching equation, where this thing here is the curvature of the unique connection that is compatible with the holomorphic structure, unique HR connection compatible with the holomorphic structure of E, the Chern connection. And and this thing here is now to this tau H is a conjugation that involves the anti-holomorphic involution that you have here using the real form, and a conjugation that goes from the usual conjugation on the Riemann surface, going from 1-0 forms to 0-1 forms. So in the familiar case of SL and C, this term here is just, remember, phi star, the adjoint, right? So this is the generalization to that. And so the theorem says that that the GR-Higgs bundle is polystable if and only if there exists a reduction of a structure group satisfying this equation. So that's how polystability appears, right? And if that reduction, the connection is irreducible, then that corresponds to the Higgs bundle being actually stable, okay? Yeah, so this is a theorem that was originally proved by hitching for SL to C, and then Carlos gave a very general proof for any group, and in fact in higher dimensions. And in this sort of language, I'm using this stability, a direct proof given with my collaborators, Steve Bradlow and Ignacy Mundet and Peter Gotten over the years. In fact, in the more general context of general pairs that I told you, in particular applies to this situation.
So what do you mean by direct proof? Not using what is direct?
This is the kind of, this theorem, now perhaps links with your question before. This theorem, not formulated as a problem for a metric, but rather fixing the metric and thinking of solving for a connection in a Higgs field, right? Thinking in that way, which is an equivalent way of thinking of the problem, right? So here we're fixing the holomorphic structure of E, and we're looking for a metric in a gauge theoretic context. You fix the reduction, and you're looking for pairs of a connection, HR connection and a Higgs field. And in that context, this theorem tells you that the quotient of those solutions by the compact gauge group is isomorphic to the stable pairs modulo the complexification of that group. And that is, if you want, an infinite dimensional version of the Kempf-Ness sort of theorem. Yeah? But there is no GAT in infinite dimensions as I know so far. And so this is a theorem that has to be done using analysis, right? And that analysis is Actually, this is a generalization of the Narasimhan-Seshadri theorem here, right? And so that take Donaldson's proof of that theorem, and then all the sequence that follow that, the Donaldson, Uhlenbeck-Yau, and then the state of the art was marked really by Carlos' approach, which just took the right analysis and all the right bounds, analytic bounds, and that we have all modeled our proofs on the proof given by Carlos, and in the context of Higgs bundles. Okay, so this you have to do analysis to prove this. Okay, I won't get into that, right? But
what's
that's
the difference between the 2003 and the 2009?
So the 2000 is about in the 2003 we didn't deal with polystability. It's only just reducing to stable and simple. In the other we dealt with polystability, which is a rather sort of complicated thing, right? Yeah, you have to prove the existence of the generalization of Jordan-Helder reductions to this context, and so that was the difference. And I mean, and also Carlos, I mean, gave a proof of this. Perhaps you can clarify it later, because I mean, basically, Carlos's approach for general groups is by embedding the group in GLN, right? And so
some kind of Tanakian.
That's right, some kind of Tanakian, and then some real structure on the Tanakian category, and so on. So what I meant here, what I mean by direct proof, is that we don't do that, right?
That wasn't solving the equations directly.
Exactly, solving the equations. So you basically solve the equations for GLNC or SLNC, and then by Tanakian considerations, you prove all these theorems. And in fact, the one I'm going to come now, the non-abelian Hodge theory correspondence, because this is only half of it, right? But we took a direct approach. I think you never used the definition of stability that I gave here, but
I don't think I ever talked about moduli space for real.
But
there was
it's
the real Tanakian thing.
Yeah.
But there wasn't the moduli space for the real case.
Okay, let me say that, no, there was no, but let me say that when I say direct approach, and also that applies to the construction of Alexander Schmidt and so on, is precisely doing that, okay, putting, constructing the moduli spaces and talking about the moduli space, and what is the stability condition proper, right? And so, but from many points of view, because polystability is actually of the, I have defined you here a precise definition of, well, I didn't define the precise definition of polystability, but there's a precise definition. But at the end of the day, polystability, which is what matters for the existence of solutions, if you just care about polystability, is just equivalent to the polystability of the GLNC bundle when you have embedded, right? If you care about stability and these finer things, you have to go to the precise definitions, okay? Right. Now, so, precisely. So this is now coming back to the relation of this moduli space of Higgs bundles for the group GR and the character variety that I defined you at the beginning. So this is the crucial result that if S is a smooth compact surface and you choose any complex structure on S, right? So that X is a Riemann surface, then there is a homeomorphism between this variety and this one. And very often there's more than a homeomorphism, but I just care about the topological map here. And so this correspondence here, the non-abelian Hodge correspondence, is actually proved by using the previous theorem together with another theorem, which is, so basically, if he is polystable, this should be GR-Higgs bundle. Sorry about this. And H is the solution to the Hitching equations. Then you can construct this connection, which is now a GR connection, right? And then the holonomy representation you prove is reductive, right? This is one direction. But the other direction is actually provided by another theorem. Now you need to prove another existence theorem for nonlinear PDEs, right? And this is the existence of a harmonic metric on a reductive flat GR bundle. So if you have a representation of the fundamental group of S into GR, that corresponds to a flat GR bundle, and now is proved by Donaldson in the case of SL2C, and correlate in general, that actually reductivity of the representation is equivalent to having a harmonic metric. And harmonic metric, actually, let me just say, what do I mean by a harmonic metric is that when you have your Riemann surface, you have the universal cover, let's say, and you have now, so the metric is actually, can be, the metric H can be thought of as actually a map from the universal cover to the symmetric space defined, yeah, and so this is, let me call H tilde. So, and this map is actually pi1 of x equivariant. And pi1 of x, of course, acts here by deck transformations and acts here by the representation rho. Okay, so pi1 of x acts via the representation rho. And so to say that the metric is harmonic is to say that this map is actually harmonic, right? And where I am taking actually here, because I'm working on a Riemann surface, on a surface I just need the conformal structure, and so the complex structure gives me a conformal structure, right? And I have here a natural Riemannian symmetric metric, right? And so it's harmonic in that respect, okay? So combining these two theorems, right, you obtain this non-abelian Hodge correspondence, which of course you realize it is as such, is a generalization of the Narasimhan-Seshadri theorem for any real group, in particular complex groups. The only difference is that in the Narasimhan-Seshadri and in the Ramanujan generalization, you don't need this part. There is no Higgs field, right? And so therefore, there's just one theorem, the previous one solving Hitching equations, okay? Yeah. Now, any questions about the non-abelian? So I won't tell you more about the non-abelian Hodge correspondence. This could be actually a full semester course to give details. And by the way, I am going to mention something before I forget. There is a reference where you can find, in particular, you can find references to papers and things about my talks here, in particular, the first talk today. And this is this paper, which is called, this is a survey paper, Higgs bundles and higher Teichmuller spaces. And here is the archive references, this. And this is about to appear, or maybe has appeared already, but let me just say to appear in the in a handbook on Teichmuller theory. I think it's Teichmuller theory or Teichmuller spaces, I don't remember now, but this handbook has many volumes. This has been, many volumes, yes, this is edited by Athanase Papadopoulos. So I don't claim that this is a survey paper. I don't claim that I gave proofs, I gave more details, but I gave plenty of, actually the bibliography is quite large. So you can look there for papers to substantiate the things that I'm explaining today. Okay. All right, so let's get into the, so this, from the point of view of representations and Higgs bundles, there are natural topological invariants that you can associate. So first, let me look at a representation. And so, as I said before, if you have a representation, you can associate a flat ER bundle defined by taking just the usual, the trivial GR bundle over the universal cover and just quotienting by rho, right? And by the action of pi1 of s, precisely as I said before, in fact, and you do get a flat GR bundle. And so the this is a very basic thing that, in fact, is general for any manifold, not just for surfaces, that the set of conjugacy classes of representations of the fundamental group in GR is the same as the cohomology set, H1 of SGR, that parameterizes isomorphism classes of flat ER bundles, right? And this is just a cohomology set in general is not a group unless GR is abelian, okay? And so now, using the, you take now GR to the universal covering of, oh my goodness, don't look at it. You are spoiling my talk. Okay. So there is a universal covering, GR tilde of GR, and you have this short exact sequence, and then this gives rise to a cohomology sequence of pointed sets, as I said before, because these are not generally groups, right? And so, however, this here, the fundamental group of any Lie group is abelian, right? And so this is really a cohomology group, H2, and in fact, because we're on a surface, this is isomorphic to pi1 of GR, right? And so the topological invariant that you associate to a flat GR bundle, GR is connected, is an element in the fundamental group of GR, right? So if we were working for, let me say, GLNC, this is the first Chen class, okay, that you're associating. And so this class, as I said, is an element in the fundamental group, and of course, this topological invariant of the representation measures the obstruction to lifting the flat GR bundle to a GR tilde bundle, right? So if that is 0, then you can lift it. So that is the topological invariant, is the natural topological invariant, so generalization of Chen classes that you can associate, right? For example, if you are with SLNC, that is always 0, right? So there's always, because SLNC is actually simply connected. So there is no, this short sequence is just trivial, okay? And so we can fix that topological invariant and define a subvariety of the moduli space by fixing this topological invariant, this characteristic class, if you prefer to call it, by being C, okay? So this is how you define topological invariance from the point of view of representations and then connecting to flat GR bundles. And now let me tell you how you do the similar thing for Higgs bundles, right? And now you have a GR-Higgs bundle, and so this is over X, and now it's a question of classifying H bundles over E, right? And and you have a similar argument, except that now you are dealing with isomorphism classes of H bundles. This is a cohomology set. Now this underline H. Previously, I didn't put any underline because the sheaf that was in the previous thing. So in the previous situation, this was thought of a sheaf of locally constant things because we are talking about flat bundles, right? Not any GR bundle, but flat. So this was locally constant. I didn't put any bar. But now we're dealing with H bundles, right? H is a complex group, and what I have is then that isomorphism class of H bundles is parameterized by H1 of this, and this is a sheaf of functions from X to the to H. Okay, and so similarly to previous case, if you take the universal cover of H, you have this exact sequence of pointed sets, and again, now you have this thing that a topological invariant of the Higgs bundle, which is actually the topological invariant of the bundle. The Higgs field doesn't play any role in defining the invariant, right? Is an element in the fundamental group of H. And so you can now define the subvariety of the moduli space by fixing this invariant, okay? It's like fixing the Chen class, right? If you were working with GLNC or something, yeah? Now, of course, the fundamental group of GR, so GR retracts onto the maximal compact, HR. Yeah?
In your definition, you said G was semisimple. Why do you restrict semisimple?
No, I did not restrict to semisimple. I could have, I said at the beginning that I could have considered reductive groups, right? And the theory extends to that. What is the difference? The difference, as usual, is that the statements about linking to representations is not representations of the fundamental group, but rather some universal central extension of the fundamental group, right? For example, if you take GL and C, you are not interested only on the bundles that have degree 0. You may want to have arbitrary degree. And of course, those do not correspond to representations of the fundamental group because automatically the degree would be 0, right? There is a slightly larger group, right, which is a central extension, right? And so the whole thing, everything I'm saying here can be extended to that by appealing to this universal central extension of the fundamental group, which is also a genuine, what is called a surface group, perfectly interesting from the point of view of geometric group theory and so on, but it's a bit more complicated theory. Everything simplifies, as usual, more when you take simple groups. That's why they're called simple, maybe. And yeah, and also I'm taking a connected group. If the group was not connected, then there are other topological invariants involved that have to do with reducing the bundle to the connected component of the identity. In fact, it's quite interesting, and this will be an important part of the theory, that even though we are starting with a this is very funny, we're starting with a semi-simple group connected, will end up naturally in groups that are non-connected and that are reductive and not semi-simple in a natural way. But we will see this, how that emerges. Yeah? So yeah, so fixing this to invariance, so what I was saying is that the fundamental group of GR and the fundamental group of H is of course the same because both retract into the maximal compact HR. HR is both a maximal compact for GR and for H. This is the beauty of this theory, that somehow why there is these two things talk to each other, basically. And not just from this point of view of invariance, but from the point of view of the theory is that a reduction of a structure group from GR is to HR, maximal compact, and the same for H. So that is exactly why the two theorems, the Corlett and the other theorem, just combined. So there is a result of Ramanujan. So when GR is compact or complex, then it turns out that this invariant parameterizes components, okay? And I have I mean, for complex groups, this was Jun Lee. With Andre Oliveira, we extended this to non-connected groups. That's why I put this here. But for this point of view, is Ramanujan, and then for complex groups, Jun Lee. Connected components are parameterized by this invariant. But the story is very different when you consider real groups that are non-compact and non-complex. And so, in general, you have a map, right, from the map from the fundamental, from the set of components to the fundamental group of GR. This is, but in general, this is neither surjective nor injective. And this is exactly the focus of the problem that, this is the starting point, in a sense, of the problem that I want to consider. And so let me explain the simplest case where this fails, and in fact, the situation that we really want to generalize, which is so the simplest case is the group SL2R. Right? Now, this topological invariant here for SL2R, so the fundamental group of SL2R is Z. I mean, the maximal compact of SL2R is SO2, the circle, right? U1, if you prefer. And so the fundamental group is Z. So there is an integer that you associate to representation in SL2R. And this integer is, I say basically the Euler class because sometimes is a multiple of this thing. But it's basically the Euler class, which is called the Euler class. And so if you fix this invariant, this integer, you have the space RD, right, in the character variety representations, we have Euler class D. And so there is a very nice, I mean, it's a very old result of Milner in 58, which proves that actually this space is empty unless the degree is bounded by the genus of the surface -1, right? So this kills surjectivity in the previous map. So not every invariant occurs, right? Which, if you're a complex group person, you see that all the invariants occur. They are always non-empty, the moduli spaces, right? Ramanujan shows that, right? But in this situation, that doesn't happen, right? Question?
Yeah. Can you look in retrospect, and can you kind of say that Milner somehow or other knew about Higgs bundles in some way?
Well, I can even go farther back and say that Cartan knew about Higgs bundles, and in the sense that there is one picture that has to do with conjugacy classes of the real Lie algebra, and the other under the group GR, and the other has to do with conjugacy classes of the isotropic representation under M under H, right? And so is the question about describing real forms as conjugations or composing the real form with another compact, compact conjugation, the one defined in the compact real form, and obtaining a holomorphic involution. So why I'm saying this is that, in a sense, I mean, Cartan knew about these two pictures, right? Now, Milner, of course, Milner knew about many things, and the question that Carlos is asking is whether retrospectively, in a sense, Milner knew about Higgs bundles, right? If you look at his paper, I look at his paper, but I honestly forgot, it's really an obstruction theory and so on, right? And constructing a connection explicitly. And so he certainly knew, you don't see the transition to this transcendental point of view, right? But who knows, you know? But in any case, this is a pioneer sort of kind of thing. I mean, there are two fundamental groups that, I mean, no, sorry, not fundamental, but two groups that you want to study after you understand Jacobians, right? The story of abelian groups. Then one is SU2, that's not a Siemens psychiatry, and the other one, and Mumford, and the other one is SL2R. And so, if you look, I mean, Milner in 58, right? So already care about this, right? I don't know what his motivation was, but it was for him the paradox in a sense of finding a connection in a flat bundle that actually that was not. So in fact, on the line bundle, it was not flat. So in that sense, he knew about Higgs bundles because the non-flatness is reflected in the Higgs field, right? Yeah. So we should look back at Milner's paper and see, you know, try to answer your question better.
Just going back to the previous thing. So you have an isomorphism of the connected components with phi 1 of the group.
Yeah.
In the compact case. So that means the left-hand side has a group structure, right? Is it obvious what it is? Is it induced from?
It's just yeah. I don't know. Yeah, if pi 0 of a topological space generally doesn't have a group structure. In this case, it does. Whether you can find this in a I don't know. Yes, maybe there is a direct way of finding that group structure on the set of components, right, of the moduli space. Yeah.
Or is it like the loop space of something homotopically equivalent to, you know?
True. Yeah. It does appear in that way. In fact, yes, also. But I mean, that's how the invariants appear also. But I don't know if you can, you know, how do you show that group structure purely from the point of view of that space? I don't know. Yeah. In fact, I was driven by that idea, and I remember giving a talk and saying, "Oh, this is this homomorphism of groups, right?" And someone said, "No, this is not a group." You know, I said, "Of course not." And so this is a map, right? And it's just not injective and surjective in general, as we just saw. For SL2R is not surjective. Right? I'm going to illustrate actually now that in fact it's not injective either. Right? And so here is, for the non-surjectivity, Milner result gives us this bound. And then let me just actually use Higgs bundles, right, to explain the non-injectivity. And so an SL2R Higgs bundle, remember that SL2R is isomorphic to SU11. And I told you before what an SU-PQ Higgs bundle was. There were two vector bundles, V and W, right, whose the determinant of one was the inverse of the other. But because we are in SU11, in fact, we have L and L minus 1. And so you can get rid of L minus 1 and to say that an SL2R Higgs bundle is a triple of a line bundle, and then a Higgs field given by two pieces. Beta is a section of L, the square of L tensor K, and gamma of L minus 2 tensor K. And or equivalent, you can associate the SL2C Higgs bundle as defined by Hitching, right? In fact, this analysis of SL2R was done by Hitching in his original paper, right? And in fact, you can, first of all, let me, before I get to the non-injectivity, that Milner's inequality follows immediately from the semi-stability of Wi-Fi. So I am not going to give any proofs basically in these two lectures, but this is the one proof that I can give because it's so easy. Let me show it to you. I mean, of course, Milner, this is not easy at all. I mean, at least for me, but it's easy once you know the equivalence, right? Which is not easy, of course. And but let me just show how you can prove Milner's inequality using Higgs bundles. And so just without loss of generality, you may assume that degree of L is actually positive, right? The same for negative. And now suppose that actually that Milner inequality is not true. Suppose that the degree is actually bigger than G minus 1, okay? So then notice that if that happens, then gamma is actually 0 because this is a line bundle of negative degree, right? So this implies that gamma is 0. And then if gamma is 0, you put 0 here, this is telling you that L is, then this implies that L is a phi invariant. It's a bundle of L plus L minus 1. And this, of course, has degree 0, but this has positive degrees. This violates semi-stability. This cannot happen. This violate. I mean, I'm assuming the stability. Excuse me. I'm assuming the semi-stability of the Higgs bundle, right? So I'm assuming that L beta gamma is semi-stable, and so this implies this violates this semi-stability, or stability if you want, right? So in fact, we will later on present a very vast generalization of the Milner inequality, and the Higgs bundle proof is always something like this. But in this example, it's extremely easy, right? But don't be misled. I mean, it's easy after you know the non-abelian Hodge correspondence, which is not easy at all. I mean, it's a very deep, there are two very deep theorems there, right? Okay, so but let's get now to the injectivity issue. And so Goldman, not using Higgs bundle, some other sort of topological approach, geometric approach, in fact, proved that RD is, so you got more in detail into these different values of the topological invariant, proved that is connected if the degree is smaller than G minus 1 in absolute value. D positive, D negative can be just, there is a duality. I mean, you can go from D negative to D positive. You can see L plus L minus 1. You can switch the role, right? So you can think, just fix the think of D positive, for example. But so here is the other situation, which is that RD has 2 to the 2G connected components if D is G minus 1. So this is the non-injectivity thing. So there are you fix the topological invariant to be G minus 1, and there are many components. So these are components that are not determined by the topological invariant, right? Like in the case of compact group and so on. And now, all this can be proved, in fact, in the teaching approach using Higgs bundles is one of the few examples where you can have a very explicit description of the moduli space of Higgs bundles. And that exhibits explicitly why there are all these components, right? And also exhibits explicitly why there is actually this is connected when D is smaller than G minus 1. And in fact, Hitchin shows that how any of these 2 to the 2G components can be identified with the holomorphic sections of the square of the canonical bundle, right? And now, but here is the other important focus that I want to make. So this is on the one hand exhibits components that are not identified by the topological invariant, but sorry? No. Yeah, exactly. These are actually square roots of the canonical bundle, if you want, or square roots of the trivial bundle. You'll see later on how they appear in a sense as square roots of the trivial bundle, in fact, which are 2 to the 2G, okay? And so spin structures, right? And this is how you actually construct these components, right? Okay, let me say this. So you call this maximal when D is G minus 1. And so here's the important point that I want to emphasize, that each of these components, right, consists entirely of Fuchsian representations. So Balaji was telling us before about Fuchsian representations, and so these are exactly representations that are discrete and faithful, and that Goldman showed that in fact those components, any of those, can be identified with the Teichmuller space of the surface. I mean, from the point of view of representations of the fundamental group into SL2R, they appear as holonomies of hyperbolic structures, right? And this sometimes referred as the, in that sense, the Fricke space, right? Some conjugacy classes of the holonomies and so on. That is with lingual representations, but thanks to Riemann's uniformization theorem, that is same as complex structures or conformal structures, right? And so any of these components can be identified with Teichmuller space of S, right? And in fact, you can say, oh, but a Teichmuller space is there's just one Teichmuller space and not what are you saying here? And from the point of view of Teichmuller theory, the relevant group is actually PSL2R, right? And so when you go to PSL2R, all these 2 to the 2G components get identified to one component, right? So you get rid of this choice of the theta characteristic, right? The square root of the canonical, and you have just one. Exactly, it's a question of lifting, and so you can lift the one in PSL2R in these 2 to the 2G ways, right? And so from the point of view of Teichmuller theory, there is just one, but if you care about a group, I said, no, I want SL2R, you can see that there are these 2 to the 2G connected components, and you see the failure of injectivity, right? But so I want to emphasize failure of injectivity and the fact that there are special components that have, if you go to PSL2R, one component that has this property of representations consisting of entirely of discrete and faithful representations, okay? Okay, so this is the question exactly that somehow gives rise to these lectures, which is whether there are other simple groups, right, with similar features to this of SL2R. By similar features, we mean exactly these two phenomena. First, the moduli space has connected components that are not distinguished by the obvious topological invariant that I defined, first. And second, whether there are components that consist entirely of discrete and faithful representations? And if so, what is the geometric significance of those components, right? And necessarily, as you realize that those groups cannot be compact and cannot be complex, right, for the reasons that we explained before, right? So they are looking about non-compact real groups that have these properties. Okay, that is the question that somehow one can ask, right? So some people were asking themselves this question, and certainly Hitching was asking himself this question, and in fact that gave rise to the first class of groups for which you can find examples of this, and that is the split real groups. So these are, remember, if you have a complex simple group, there are many real forms, as we saw for SLNC. You have, SUN, SLNR, and SUPQ, but there are always one which is compact, SUN, and one which is split, which is SLNR. So the one which is more compact, the one that is less compact, and very often in between there are others, right? So, but for the split real form, so we'll see that one can find components like that. And then the next class of groups for one can be able to detect the existence of these components are groups of Hermitian type. These are groups in which the symmetric space here, GR mod the maximal compact, is actually Kähler, right? Has a Kähler structure. And so, of course, SL2R shares both properties. It's both a split real form of SL2C, but is also a group of Hermitian type. And of course, the symmetric space here is the upper half plane, if you want, hyperbolic plane, or if you think of SL2R as SU11, is the Poincaré disk, right? And so this, so SL2R is actually SL2R is certainly at the intersection of these two classes of groups. We'll see more that is somewhere else, but that will come later. And so this, so let me start. Right? Well, for the split, the split group. What I'm saying, yeah, for the split group, precisely, the split real form, right? In the Cartan decomposition, you can have the maximal abelian subalgebra of GR entirely contained in MR, right? So this is what, or as I said in a more colloquial way, is the less compact of all the real forms. I don't know. You have another class of groups in mind? I'm a bit confused about. Okay. Well, perhaps we can discuss this. But certainly, the split. So what are the split real forms, right? And as I said, for SL and C, you have SL and R, and then for so for the classical groups, for the complex symplectic group is the real symplectic group, and then you have for the orthogonal group with even, you have SONN or an SON, comma n plus 1. These are examples of groups that are split real forms, right? Yeah.
You have to, sorry, at the top there, do you have to say maximal abelian subalgebra consisting of semi-simple elements or something like that?
No, you don't.
If you just take the upper triangular ones, you have like n squared, n over 2 squared or something like that. You have ones of size n over 2, n squared over 4.
You always have in a real form, for any real form, you have always a maximal abelian subalgebra here, right? Which is very important, right? But what I'm saying is this
doesn't necessarily mean maximal size. It means maximal, but there's no bigger one.
There's no bigger one, yes. But the point is that what distinguishes any other real form from the split one is that this is a maximal abelian subalgebra of GR itself. Right? So
you don't need to say something to rule out maximal, but which are unipotent abelian subalgebra?
I don't think so. No. So you can find, in general, you have some piece for the maximal GR, you have a piece here and a piece here, but in the split one, everything can be here, right? Sort of that you can find that. The other, yeah. No, I don't think you need to add anything. So, so these are the examples, and then, so here, let me tell you how Hitching actually constructed these components, at least for SL and R, right? And so the main ingredient in Hitching's construction is actually considering the Hitching map. And so let me explain. You have now take the the Lie algebra of SL and C, right? So these are matrices of trace 0, right? And consider the coefficients of the characteristic polynomial of a matrix, right? So these polynomials here are polynomials, homogeneous polynomials of SL and C that are invariant under the action of SL and C, right? And have, you know, the degrees given by I plus 1. And so now you go to the moduli space for the complex group, right? And you have the Hitching map, and that evaluate this polynomial invariance, these invariant polynomials, excuse me, in the Higgs field, and you end up in actually in this vector space, which is direct sum of sections of these powers, k plus 1 of the canonical line bundle. And so this has half the dimension of this space, right? And of course, there's a fantastic story about this integrable system and so on, but this is not the focus of these lectures today and in this mini course. But the fact that was important is that Hitching constructed a section of this map by using constant triple, and that section gives you, describes a full component of the moduli space of the Higgs bundles for SL and R. So it's actually a component of the character variety for SL and R, right? And so in particular, for SL to R, you do get, in fact, sections of the square of the canonical bundle, and this is the usual identification with the Teichmuller component that I mentioned before for SL2R. Okay, so this was a generalization of that. So Hitching gave a construction of that for any split real form. Okay, and then with my former student Anna Peon, we actually gave a general construction for any real group, for which you can actually define the Hitching map, and then you get a section of that uses the theory of triples by constant rallies, and not just the constant triples, but constant rallies that are adapted to a real form. And in particular, by doing that, you don't need to go to the moduli space for the complex group, but directly work with the Hitching map for the real group, and you get actually the section also, and that is a component of the for the real group. Anyway, but so this is how Hitching constructed his components as sections. So they are topologically trivial. They are vector space, right? And they are smooth in particular, and so already from Hitching's construction, you can see the following: that every representation in the Hitching component, I say the Hitching component because if you assume that the group is adjoint, right, like PSL and R, there is just one component, right? Otherwise, there are maybe several components, okay? But for any of those, I mean, so every representation can be deformed to a representation that factors in this way. You go to the, you have the so-called principal representation of SL2R in GR, right? And the representation deformed to one that is a Fuchsian representation here. So it's a Teichmuller is something in the Teichmuller component, and then composed with this representation that this principal representation that was constructed by constant, that one always has for the split groups. Right? Reducible representation of SL2R in GR, right, when GR is split, okay? And so in a sense, I mean, what happens is that any representation that deforms to something which is really in the Teichmuller space, in the usual Teichmuller space, because it is a representation into the Teichmuller component of representations in SL2R. Right? But of course, that deforms to representations to a whole moduli space that has the right dimension, right, and higher dimension. So later on, Laborie actually showed that, in fact, I was suspected by Hitching, or was asking this question, that any representation is actually, there is discrete and faithful, okay? And I will come back to the, I mean, he was using a Nosov, the notion of a Nosov that he introduced. I'll come back to that later on, okay?
When you say Hitching component here, you mean the image of the section?
Yes, the image of the section, you take this section, and so you see this vector space, right, giving you a component of the moduli space of Higgs bundles, right, in the moduli space for that, of Higgs bundles for that real group, and by the non-abelian Hodge theory that is representations into that real group, and so it's a full component, and I mean, yes, a Hitching component is that component, a section of, yeah?
But then what does it mean to be unique? I thought, so there were these other components you were looking
Yes,
at.
what I said is that, if you work with a group that is of adjoint type, so you're killing the center, right, then this is unique, right? The Hitching component is unique. For SL2R, we saw that it's not unique, but if you consider PSL2R, you do get just one component, okay?
Yes,
What I'm saying, actually, okay, if the group is not of adjoint type, there are different sections, which in fact, again, these different sections come out to be choices of spin structures, right? To choices of square roots of the canonical bundle, okay? So what happens is that actually the Higgs bundle is a bundle and a Higgs field. And the bundle is, in all these cases, is some vector bundle that, for the classical groups at least, let's say, that is constructed from some square root of the canonical bundle. And there are 2 to the 2G choices, right? So if you kill the center, right, so you get rid of these choices, right? Or in other words, you do have different sections, right? And each of these sections has the properties that each of these components have these properties that I'm saying, right?
saturating the bound that you had earlier?
No, there is...
G less than G minus 1, the analog of that?
No, you know, for that bound was a privilege of SL2R, because SL2R, you'll see that that integer invariant came from the fact that the maximal compact of SL2R is a circle, so there is an integer, and that integer was bound. If you are in SLNR for n bigger than 2, the maximal compact is SON, right? And so the topological, the fundamental group is no longer the circle, right? And so you don't have this integer, right? You'll see this integer is a privilege of not just being split, but of not a split case, but of being of Hermitian type. Some groups are both split and Hermitian, like SL2R. And in fact, the only group in higher rank, basically, that has this property is this guy, sp2nr. Oh, again, I'm giving you the answer in the, so sp2nr is both split and Hermitian. So it's not, so in this general construction of Hitching, there's no, so in general, there's no integer, right? And it's just that you have the Hitching map that you always have, and he constructs a section, right? And the section happens to be a component of the moduli space for the split real group, right? Of representations for the split real group, okay?
So the moment it's just a construction, and you're saying that saying it's unique means that construction produces just one section.
I'm saying that actually you can construct, in general, several sections. Yeah. And each of these sections maps from the base to the moduli space is a connected component. If your group happens to be of adjoint type, all this collapse into one, right? And so the uniqueness, I think I even mentioned, perhaps let me go a bit farther here. The Hitching component is unique if GR is a split form of adjoint type, right? So there is unique. Otherwise, there are choices, and you have several, and all of them are perfectly decent components of the moduli space, and each of them enjoys the property that consists, from the point of view of the representations, are discrete and faithful representations. Okay? Yeah? So there was this question about what is the meaning, the geometric meaning of this in fact, Hitching asked this question, what is, here we're having something that in a sense generalizes Teichmuller space because of consisting entirely of discrete and faithful, but and we know how important Teichmuller space of a surface, the usual Teichmuller space is, in the sense that linking to three manifolds, and also linking to the Riemann's moduli space if you take the quotient of Teichmuller space by the mapping class group, right? So here is another class of spaces that maybe parameterize some interesting structures. And so Hitching asked precisely that question at the end of his paper in '92, right, when he gave this construction. And there had been previous work actually by Goldman and Choi for the case of PSL 3R, and there they showed that they parameterize convex projective structures, right, and on the surface. And the answer to this question, or some answer to this question for more general split real groups, is still quite mysterious. There's some work by Guichard and Winhard relating this to some geometrical structures modeled on certain homogeneous spaces. I won't get into that, but that's a very interesting direction of understanding what is it. In general, they are not things on the surface. There is no space on the surface of this, but higher dimensional things, right? But must be quite fundamental somehow. Okay. Still have 5 minutes, yeah? Yeah, okay. So let me just at least say something. I was hoping to say more, but let me get to another class of groups for which you can do things. And this is the groups of what I call of Hermitian type. And as I said before, these are groups that are characterized by the fact that they have a complex structure, and the Riemannian metric that is symmetric is actually Kähler. Right? I don't know why I call of Hermitian type. They should be called of Kähler type, because really, because of homogeneity, these are Kähler really, right? And so a characteristic of this is when GR is simple, not semi-simple, simple, right, is that the center of the Lie algebra of HR is one-dimensional, is R. And actually that is what defines the complex structure on this space, right? Via the isotropy representation. The tangent space of this is actually MR. And so you can define, by using this element in the center, define a complex structure. And so this means that the complexification of MR that was, remember, the complexification of MR is this M here, decomposes in the 1-0 part and the 0-1 part, right? And so this is the example of SUPQ that I was telling you at the beginning. And of course, SL2R, because SL2R is SU11, right? And, but here is a list of the classical groups, connected groups of Hermitian type, right? With SUPQ, then the real symplectic group. This is both, as I said, a split and Hermitian, right? And then there's a real form of SO2NC, which is this is called the non-compact dual of SO2N, and then this other real form. These are and then two exceptional real forms using the Helgeson's notation is one real form of E6 and one of E7. These are all the real. I mean, of course, you have considered covers of this, right? Finite covers, but in terms of Lie algebras, these are the only groups of Hermitian type, right? And for which you have this phenomena, and so for which what happens is that the isotropy representation decomposes into these two pieces, and so the vector bundle where the Higgs field takes values decomposes always like this, M plus M minus, and so you always have like two Higgs fields, right? One in M plus, another one in M minus, and so then, similar to what happened to SL2R, right? There is the fundamental group of H is actually isomorphic to Z. I say here most of the time because sometimes there is a torsion element, right? But in particular, in fact, of the list that I gave you before, that only happens the existence of something that has torsion only happens for this group here, right? And because the maximal compact has also an SON here, and so this is the, gives you some torsion thing. But in particular, you always have that there is an integer that you can associate to a Higgs bundle or equivalent to a representation, right? And this integer is, I say essentially again because there is maybe some multiple, some normalization that you fix, right? But it is, and this is the Toledo, is called the Toledo invariant, Domingo Toledo. And so here is a generalization of the Milner inequality that is this Toledo invariant is bounded by the rank of the symmetric space, or the rank of the group if you want, times the genus minus 1, right? So of course in the case of SL2R this is 1, right? So we recover the Milner inequality. And this was proved over the years by Domich, Toledo, and Turayev also gave a proof for this real symplectic group. And then from the point of view of Higgs bundles, in collaboration with Steve Bradlow and Peter Gotten. And in our approach is always similar to the case that I was explaining of SL2R, that is using semi-stability, except that it's definitely not as easy as in here. And in fact, so a general proof of this, I mean for general groups, not just classical, for any groups, was given by Burger, Yossi, and Winhardt using bounded cohomology, and the Higgs bundle proof in my work with Olivier Bicard and Roberto Rubio, again, is always this kind of thing, but it's much more difficult. And yeah, so I think okay, so you have this bound here, right? And so I want to show you tomorrow that as in the SL2 case, when you consider the maximal value of this invariant, that is the rank of this times G minus 1, there are also components that deserve to be called higher Teichmuller components for the reasons that they are not determined by the topological invariant, and also because of the dynamical properties and the fact that the representations there are discrete and faithful. Okay, and so that will come tomorrow.